Welcome back to another video with us here at LMDN STEM Academy. In this video, we will be continuing our work on the Module 1 question. So it's question 1 part F from the Cape Chemistry Unit 1 Paper 2 from June 2024. Now the question is a question on the mole concept and specifically titrations. So it says that potassium nitrate, KNO3, decomposes on heating as shown in the equation below. So here we have an equation that says 2 moles of potassium nitrate is going to get broken down into 2 moles of KNO2 solid and a mole of oxygen gas. So a sample of KNO3 weighing 6.02 grams, so this guy known as sample A, was partly decomposed on heating. The residue, right, of that decomposition was dissolved in water and made up to 1 dm cube of solution, right? Then 25 cm cube of the solution was pipetted into a conical flask and acidified with equal volume of dilute sulfuric acid. The mixture was titrated with 0.02 mole per dm cube of potassium manganate 7 solution, and the average titer was found to be 27.50 centimeter cube. Now, this is a lot of words, and it might be hard for you to really see what is going on. So I often suggest to my students at this point that you're supposed to just draw a nice little picture, an image to help you to really understand what's going on. So we're going to do that and just run through these lines again, okay? So let's just sketch. I'm going to sketch down here. Right? So we have our KNO3 that weighs 6.20 grams, right? That was partially decomposed on heating. You can imagine that we have the 6.20 grams of KNO3, right? We break that down partially. So I'm going to put partially there. And that gives us our residue. Right? Partially decomposed, we have a residue that gets left behind as a result of that. That residue, right, is then taken and dissolved in water, and that's made up to a 1 dm cube of solution total, right? So you have your residue that you take and you put in water, make that up to 1 dm cube, right? So the idea here is that this residue is this solid here, that's KNO3, right? So we can make that leap at this point. So that's KNO2 there in that residue. We'll put that in water, make it up to 1 decimeter cube, right? Then what's gonna happen? We're gonna take out of this solution now, which is residue dissolved in 1 dm cube of water, we're gonna take out 25 cm cube out there. Okay, so we're gonna take out 25 cm cube of that residue solution, we're calling it now. And we're gonna put that into a little conical flask, okay? So here's our conical flask, that in that we have the 25 cm cube of that residue solution, right? So then now once we have that, we're gonna add in, so I'm just gonna put here that there was some H2SO4 added there just to acidify it, okay? So we know there's some H plus ions in this conical flask. And then now, here's the key part. Now we're gonna titrate this 25 cm cube of the residue solution with 0.02 mole per dm cube of KMnO4. So we're gonna have a burette now that's gonna come into play, right? Once we're doing our titration, you know, we're gonna have our burette now that comes into play. Now it's a little bit too down in the conical flask, but you get the idea. We're gonna have a burette going down in there. And from that burette, we're gonna be pouring in our 0.02 mole per dm cube solution of KMnO4. right? And they said that in the end, we're going to end up using this much of that KMnO4. So I'm just going to put that the volume there that we're going to use is 27.50 cm cube. So this is a nice distilled version of what's going on, right? We take our KNO3, it's partially decomposed, so we get this residue of KNO2. We're going to put that in water to make a residue solution. We're going to take out 25 cm cube of that, put it in a conical flask, add some acid to it to acidify the solution, and then we're going to run a titration on that, what we call a titrated volume, right? That's our sample volume that we're titrating with. This much KMnO4, this concentration and that volume is what was used in the end. So this is a nice little picture to have in our minds as we proceed throughout this question. So let's go ahead with the question now. All right, so the first part of this question says, calculate the number of moles of potassium manganate 7 that's used in the titration, right? So remember now, these pink letters here let us know everything that we need to know about KMnO4, right? So how many moles of KMnO4 was used? If we need to find the moles of KMnO4 used, and we have a concentration and we have a volume, what are we going to do, right? If we need to find moles, it's equal to concentration of potassium manganate times volume of potassium manganate used in the titration. We know that the concentration was 0.02 mole per dm cube. We have it here and we have it on our picture as well. And we know that the volume that was used was 27.50 cm cube. We're just going to go ahead and convert that to dm cube so our units match with the concentration units. And just multiply those two things. Concentration times volume gives us moles. And so we end up with a value of 5.5 times 10 to the minus 4 moles of KMnO4 being used in the titration, okay? So what that means is from the burette, we've just dumped in 5.5 times 10 to the minus 4 moles of KMnO4 into this residue solution, okay? All right, so let's go ahead now. So the next part of the question says, using the equation that 2 moles of manganate ions react with 5 moles of the nitrite ion, so the NO2, that's acidified, 6 moles of those H plus ions, because we said we acidified it, so we know that that's there. That's going to give us Mn2 plus 5 moles of NO3, the nitrate ion, and then 3 moles of liquid water, right? So this is just an equation. It's a net ionic equation that describes the titration that's going on here, right? And so we're being asked to deduce, just make a deduction, right, about the number of moles of KNO2 that was in the titer volume. Okay, so how many moles of KNO2 was in this volume here, right? We just calculated how many moles of KMnO4 we put in there to get to that endpoint, or to see a color change. We know how many moles of that we put in there. And so we can use stoichiometry to figure out how many moles of the NO2 must have been in there. So that's what we're going to do. So it says here now that from the balanced equation, so from this balanced equation, we know that 2 moles of the manganate ion, so 2 moles of this guy would have reacted with 5 moles of the nitrite ion, NO2 minus ions, which is in our residue, right? So we know that from the balanced equation. And what we also know from the first part of this question was that 5.5 times 10 to the minus 4 moles of manganate ions were placed in to that conical flask, right? And so then we can make a correlation. Then if 2 moles react with 5 moles, and in this particular instant, in this particular titration, we only use 5.5 times 10 to the minus 4 moles, that means that there were X moles of nitrate ion in there. And we can find that by using this simple relationship, right? And so here's what we're going to do now. It's just a simple cross multiplication. So we're going to solve for X pretty much. And so let me just get a pens to show you how we cross this in case you're interested, right? we just do 5.5 times 10 to the minus 4. We cross multiply that with this 5 here. And then we would have cross multiply the x with the 2 moles, right? And so in the end, what are we doing? We end up with 5.5 times 10 to the minus 4 times 5 divided by 2 moles to find x. And that x turns out to be 1.375 times 10 to the minus 3 moles of KNO2. So that's what was in here. So I'm just going to add that in here, right? We had 1.375 times 10 to the minus 3 moles of KNO3. So that's how much was in there. And again, we found that out by correlating how much MnO4 was used with using the stoichiometry to connect everything here. Okay, and so that's our number for how much KNO2 was in there. Okay, so now we have to calculate the number of moles of KNO2 that was present in the residue from the decomposition of sample A, right? And so remember now, what we just calculated the number of moles for, right? This orange letter here, the 1.35 times 10 to the minus 3 was how many moles was in the 25 cm cube of residue that was in that conical flask. Remember, you know, we're coming from a 1 dm cube or 1,000 cm cube total residue volume, and we took out 25. So the orange number, 1.375 times 10 to the minus 2, represented how many moles were in 25 cm cube. And so now the question is asking, okay, how much was actually coming from the whole sample? How much was actually in the 1 dm cube? Right? And so to do that again, we can just use some ratio, right? If I know how much is in 25, I can find how much is in 1,000 cm cube, aka 1 dm cube. So here it is, 1.375 times 10 to the minus 3 moles was present in 25 times 10 to the minus 3 dm cube, or in that tighter volume. So I know that. So I need to say, okay, then Y moles would have been present in the 1 dm cube, or the original stock solution here, the residue, total residue volume, which was this. Okay? And so again, simple cross multiplication here again, we're just correlating the ratios here to get the value that we need in the end. And so what we're gonna do now is we're gonna say, okay, Y times 25 times 10 to the minus 3 is equal to 1 times 1.37 times 10 to the minus 3. And so when we do that cross multiplication and we work it through to solve for Y, we're going to get that Y is equal to 1 times 1.375 times 10 to the minus 3 moles divided by the 25 times 10 to the minus 3 dm cube. Okay, so again, it's just correlating the ratios. If I know how much is in 25 times 10 to the minus 3 dm cube, I know automatically how much is in 1. And so when I carry this cross multiplication through, I end up with a value of Y being equal to 0.055 moles of KNO2 in the residue. So in this big old residue up here, it was this many moles of KNO2. Okay? Again, we knew how much was in the 25, so we can work backwards to find out how much was in the bigger, the larger volume. So I'm just going to put that number up here so we can keep everything nice there while we work. So in this residue, we just found that we had 0.055 moles of the KNO2. Okay, that was formed from that partial decomposition of the KNO3. All right, so let's go ahead now and see what else is being asked. All right, so now we're being asked to calculate the mass of KNO2 present in the residue from sample A, right? So up here, this is where we're at now. Sample A, this is the residue. So what mass of KNO2 was present there? We know the moles, we just found the moles, right? So we know how many moles of KNO2 was present in the residue. So all we have to do is just convert that moles to mass. Okay, so that's what we're gonna do. So we're going to convert the moles of KNO2 present in the residue to mass of KNO2 present in the residue. So we're going to take these moles and then we're going to multiply that by the molar mass. That's how we find mass, right? Mass is equal to moles times molar mass. The molar mass of KNO2 is what? The molar mass of KNO2 is going to be equal to 39 plus 14 plus, what is this? This is oxygen, so that is going to be O2, so that's 32. And so the molar mass of KNO2 works out to be 85 grams per mole, right? So all we're going to do is we're going to take the 0.055 moles and multiply it by 85 to get the mass. And so here it is. Mass of KNO2 is equal to 0.055 moles times the molar mass of KNO2, which is 85. And so we end up with a value of 4.675 grams. All right, so I'm going to add that to our little figure as well, that this mole turned out to be 4.675 grams of KNO2. That's the mass that was present in the residue. Okay, so it says now, using the equation for the decomposition of KNO3, determine the mass of KNO2 formed if 6.20 grams of KNO2 were completely decomposed. So this is the key word here now, completely decomposed, right? Now we know from the problem statement up here that all of these, this titration that we did here was for a partial decomposition. It was only partially decomposed when we got this mass and this moles, right? That was a partial decomposition. So now the question is saying, if you have everything, all of this being broken down, right? This entire mass being broken down, what mass of KNO2 would you form in that case, right? And so how are we going to do that? We're going to use this equation up here, right? And that equation tells us that 2 moles of KNO3 would give us 2 moles of KNO2 upon complete decomposition, right? And so here it is now. So from the balance equation, when 2 moles of KNO3 is completely decomposed, 2 moles of KNO2 is formed, right? And so what it's saying now is that 2 moles of KNO3 is going to give us 2 moles of KNO2. Complete decomposition. 2 moles is a 1-to-1 ratio, 2-to-2 ratio. Same thing, right? So from the balance equation, when 2 moles of KNO3 is completely decomposed, 2 moles of KNO2 is formed. Now, because they want us to find a mass, we can convert this mole ratio to a mass ratio, right? And what that means is that we're gonna take the 2 moles of KNO3 and just convert that into a mass, right? And so that we would have gotten that 202 by saying 2 times the molar mass of KNO3, which is 101 gram per mole, right? So with the 2 moles times the molar mass of that to get the mass that would be equivalent to, and that is 202 grams. And then, of course, earlier we calculated that the molar mass of the KNO2 was 85. So if you multiply that by 2, you're going to get 170. So that's how we got that. So again, because they want us to find the mass of KNO2 formed, we're going to just take the mole ratios and then convert those mole ratios to mass ratios, right? So if 202 grams of KNO3 is completely decomposed, we're going to get 170 grams of KNO2 being formed. But for the question itself, how much grams did it say would be partially decomposed? It's 6.20 grams. So we're not going to quite do 202. We're going to do 6.20 grams, but the mole ratios or the mass ratio still holds, right? And so here's our next line. Our next line then says that 6.20 grams, right? So let's make that super clear there. That is saying now that 6.20 grams of KNO3 is completely decomposed. If that is completely decomposed, X grams of KNO2 will be formed. So again, here we are, we have a cross multiplication situation again, where we're gonna say that X times, we're gonna do X times the 202 grams is equal to that guy, 6.20 times 170. So it will be X times 202 grams is equal to 6.20 times 170. So that would mean that X is equal to 6.20 times 170 divided by 202. That's how we solve for X, right? This X gram here, cross multiplication. That's what we've been doing all this time. So here it is now. So X is equal to the 170 grams times the 6.20 divided by 202, and that gives us a mass of 5.218 grams of KNO2 formed. Again, that is if all of the 6.20 grams is completely decomposed, right? All right, so that's our number here for complete decomposition. It's 5.218 grams of KNO2 being formed, okay? So this part of the question now says, using the result from F part 4 and 5, calculate the percentage of KNO2 formed. So they're saying, okay, previously we found the mass that's formed from the partial decomposition, and this one was that one. So that one was for the partly decomposed, which we did the titration on. So if it's partly decomposed, we said that we had gotten a mass of 4.675 grams of KNO3. And then when we had the complete decomposition that we just did in part 5, we had gotten a mass of 5.218 grams, right? So this is the complete case and this is the partial case. So we're being asked to calculate the percentage of KNO2 formed. That percentage is, okay, how much could you have gotten if it went all the way? And then what fraction of that did you actually get in the partial decomposition case? So this is the formula that we would use, just a percentage of all that's possible. So it says that the percentage of KNO2 formed is equal to the actual mass formed from the partly decomposed, which is this number here, divided by the total mass formed if completely decomposed. So we're going to just put the 4.675 grams over the 5.218 grams and multiply that by 100. And so we get the percentage of KNO2 formed is then equal to 89.59%, right? So that partly decomposed only got us 90% of the KNO2 being formed, okay? So that's what that means. What percentage of KNO2 was formed? And of all that we could have gotten, we only got 90% because it was a partial decomposition. Okay? So let's go ahead now. All right. So part 7 of this question is asking us to outline the steps taken in the laboratory to prepare the 0.02 mole per dm³ of potassium manganate 7 solution that was used for the titration, right? So we had to prepare the solution in the lab before we could do that small scale titration that we did. So in order to prepare this, here's what we're gonna need to do, right? What this tells us, it tells us the concentration of potassium manganate that we need to make. And so essentially what that is saying is that we need 0.02 moles of KMnO4, that potassium manganate. We need that many moles of it to be in 1,000 cm³ or 1 dm³. Right? That's the same as 1 dm³. So that's what it's saying. So we know that we need to have this many moles of KMnO4 being dissolved in 1,000 cm³ of distilled water, right? And so the first thing that we're going to have to do in order to prepare this is we're going to have to say, okay, step 1, I'm going to need to use an electronic balance to weigh out a mass of KMnO4 solid. Now that mass, how are you going to know what mass to weigh out? Well, the mass is equal to the moles that you're going to need times the molar mass of KMnO4. The moles that you're going to need, we already established it from here because they told us that we need that many moles in 1,000 cm³. So the moles that you're going to need would be 0.02 times the molar mass, which is 158, the molar mass of KMnO4. When you multiply those two numbers through, you come up with a value of 3.16 grams, okay? So that's how many grams of the KMnO4 solid that you would go in your container containing the KMnO4 solid, and you take out 3.16 grams, and you're gonna weigh that. You're gonna weigh out that much, okay? That's the very, very first step on an electronic balance that you're gonna weigh. So then after you weigh that now, you're going to dissolve that in 500 milliliters of distilled water by stirring it with a glass rod. So you put that in a beaker, and you're just going to stir that with a glass rod, okay? Then you're going to use a filter funnel to transfer that solution that you made in step 2 into a volumetric flask. Then you're going to add more distilled water to the volumetric flask to make it up to 1,000 mils. Right? Or 1,000 cm cube, 1 decimeter cube, because that's what the final volume needs to be. You're going to stop just below the meniscus though, right? When we're making the solutions so that they're very accurate, we stop below the meniscus. We don't go all the way up to the 2,000, up to the 1,000. We're going to stop below the meniscus. Don't go all the way to the 1,000. And then we're going to use a dropper to add water dropwise, distilled water dropwise until the bottom of the meniscus is on the calibration mark on the volumetric flask, right? And then we know, okay, we're at exactly 1,000 milliliters now. And so now what we're going to do is we're going to put a stopper on the flask and shake it gently to make sure that everything is well dissolved throughout and we have a homogeneous solution, okay? So these are the steps that we would take, pretty standard steps that we would take in making a standard solution. The very important thing here to note though is that you need to know what mass of the KMnO4 solid you would need to weigh out, and you can calculate that by using what the concentration of the potassium manganate solution needs to be, and by using the molar mass of the potassium manganate, okay? And so with that, we've come to the end of this question. Definitely give this video a like, subscribe to the channel, and if you look on your left here, you'll see the next video up. And if you look on the right here, you'll find our Module 1 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So thanks for watching, and we'll see you in our next video.